Hi everyone, welcome back. So lately we've been learning how to solve systems of linear equations, and in the previous lesson we learned how to use matrices. We would write the augmented matrix of the system, and we would do Gaussian elimination to simplify the matrix, and we could solve a system based on that. So in this section what we're going to do is we're going to just look at matrices as objects of their own. Outside of just solving systems, matrices are also just useful in other areas of math. So we're going to work with matrices, and this lesson is called the algebra of matrices. Let's go ahead and get started. So in this lesson, we're going to learn how to do different things with matrices, such as adding them together, multiplying them by each other. But first, we're going to start out with what does it mean for two matrices to be equal? So we're going to talk about equality of matrices. And it's pretty much a simple definition. We're going to say two matrices are equal if they have the same entries in the same positions. So, for example, just an example of two matrices that are equal to each other. If this 2 by 2 matrix, A, B, C, D, is equal to this 2 by 2 matrix, 1, 2, 3, 4, then we must have A equal to 1, B equal to 2, C equal to 3, and D equal to 4. All of those things have to be true. They have to have all of the same entries in all of the same positions. It's not good enough to just have 3 out of 4 or anything like that. It has to be all of them. Now, something that's kind of built into this definition of equal matrices is that in order to have the same entries in the same positions, they must have the same size. Equal matrices are the same size. And when we talk about the size of a matrix, I don't know if I've said this before, but we sometimes call this the dimension. The dimension is the size. So let me underline some things. We're talking about what it means for two matrices to be equal, and now we have this term dimension. And when we say the size of a matrix, we have to say how many rows and how many columns does it have. We write, or we say a matrix has dimension m by n, where m is the number of rows, n is the number of columns. So we say the rows first. So, when I've been saying that this matrix is 2 by 2, it has 2 rows and 2 columns. Above, I said something about if these two matrices are equal. Let me give you an example of two matrices that are not equal. The matrix 1, 2, 3, 4 is not equal to the matrix 1, 2, 3, 4, 0, 0. Those are not equal. Even though all of the entries in the left matrix appear in the same position in the right matrix, we still do not say these matrices are equal because the one on the right has entries that don't appear in the one on the left. And by the way, this matrix we would say is 2 by 2, and this matrix we would say is 3 by 2. It has 3 rows and 2 columns. So as soon as I see that they're a different dimension, I can automatically say that they're not equal to each other. I'll give you another example of two matrices that are not equal to each other. 2, 4, 6, 3, 7, 12 is not equal to the matrix 1, 2, 3, 3, 7, 12. By the way, these are both 2 by 3 matrices, a 2 by 3 matrix and a 2 by 3 matrix. So they're the same size. They're not equal to each other, though. And, I mean, we can tell from what we said above about how we define equality of matrices. I mean, do they have all of the same entries in all of the same positions? No. This one has a 2, a 4, and a 6. This one has a 1, a 2, and a 3. So why am I even bringing this up? Well, the reason why I wanted to mention this is because we've been doing row reduction. We've been doing Gaussian elimination, where we, add a multiple of a row to another row, or we multiply a row by a constant. It looks like I took row 1 and multiplied it by 1/2. And that's something that we typically do when we're trying to solve a system, right? But they're not equal as matrices. If we were doing this to solve a system problem, sometimes we would draw an arrow connecting these two, right? An arrow pointing to the right, and we would say we multiplied row 1 by 1/2. It's okay to draw an arrow, but we should not put an equal sign between them, because as matrices, they are not considered equal. And I'm going to say, even though their corresponding linear systems have the same solutions. I know they have the same solutions because, you would get from one matrix to the other by doing one of those steps that we're allowed to do. Okay, but we don't call the matrices equal. So in this lesson, the algebra of matrices, we want to start doing more with matrices. Everything here so far has just been about what it means for matrices to be equal to each other or not equal to each other. And that's about all we can say about matrices being equal. Let's talk about sums and differences. How do we add matrices or subtract matrices? Well, given two matrices of the same size, where we said that the size is also known as the dimension, we can add or subtract corresponding entries. So add or subtract corresponding entries. I'll show you some examples. Let's do one example of each. I'll do an example of adding two matrices, and I'll do an example of subtracting. So let's say I want to add this matrix plus this matrix. This is the first time that we've put a plus sign in between two matrices. And this is what I meant earlier when I said we were going to be just working with matrices as objects, like mathematical objects that we can add, we can subtract, we can talk about whether they're equal to each other, maybe do some other stuff too. So all we do, I'm saying, is add or subtract the corresponding entries. I mean, this has a plus sign, so I'm going to add, when we say corresponding entries, we mean the number in the upper left plus the number in the upper left. 1 plus 6 is 7. Upper right plus upper right, 2 plus 3 is 5. The lower left plus the lower left, 3 plus -1 is 2. Lower right plus lower right, so 4 plus 0 is 4. So if you were asked to add two matrices, you just do a bunch of addition. You just add the corresponding numbers. Let's do one where we subtract. If there's a minus sign in between two matrices, this is just a little example. Okay. First of all, they are the same dimension, so we can do this. 1, 2, 3, 4, minus 2, 1, 1, 2. The upper left entry minus the upper left entry is 1 minus 2. 1 minus 2 is -1. And then we do 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 2 is 4. I'm sorry, 4 minus 2. I wrote it correctly, but I said it wrong. 4 minus 2 is 2. So that's all you have to do if you have to add or subtract matrices of the same size. What if they're different sizes? Well, I'll just say this out loud. If you're given two matrices of different size and you're asked to add or subtract them, the sum or difference is undefined. You can't do it. You can't add two matrices of different sizes. And you probably won't be asked to. But if you ever were, you can't take like a 2 by 2 matrix and add a 3 by 3 matrix to it. It's just undefined. So that's what I wanted to say about sums and differences. There's another sort of operation that we can do, and this is going to be called the scalar product. We can multiply a real number times a matrix. To do this, we scale all entries up or down by the real number. I'll show you two examples of this. So this is going to be a real number times a matrix. So as an example, let's say I want to do 3 times this matrix. It's a real number times a matrix, right? 3 is a real number. So I say to do this, we scale all entries up or down by the real number. What I'm going to do is the result is going to also be a 2 by 2 matrix where every entry is going to get scaled up by a factor of 3. So the 1 is going to become 1 times 3. Or you could think of it as 3 times 1. So I did 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. That's it. So the number out front gets multiplied by each entry, and we get a new matrix. It's the same size as the original matrix as far as dimension. It's the same size, but all the numbers have become bigger by a factor of 3. They're all 3 times bigger than what they were. Well, why did I say we scale the entries up or down? Like, how could you scale down? That would be if you had a real number like 1/2. If you wanted to do 1/2 times this matrix, well, you do 1/2 times each of the entries. The result is still going to be a 2 by 2 matrix. 1/2 times 1 is 1/2. 1/2 times 2 is 1. 1/2 times 3 is 3/2, and 1/2 times 4 is 2. So you see the entries of the matrix have been scaled down. They're all smaller now. You could even do 0 times a matrix, just all the numbers would become 0. All right, now, what we've talked about so far, we talked about what it means for two matrices to be equal, how we can add or subtract two matrices, and we talked about this idea of a scalar product where you have a real number times a matrix. What we want to talk about next is, what about a matrix times a matrix? And that's going to be a little bit trickier. Okay, so let's talk about matrix multiplication. And this is different from the scalar product. In the scalar product, we multiplied, right? I mean, that could be called scalar multiplication because it involved multiplication. But now we're talking about a matrix times a matrix. So, given two matrices, A and B, we're gonna start referring to matrices by just uppercase letters sometimes. And the question is, what is A times B? Now, I'm going to say this is more difficult than what we've done so far in this lesson. It's not as straightforward as adding or subtracting. I mean, you might think, would we just multiply the corresponding entries? But that's not how we do it. There's a reason why, but that's not how we do it. So, first of all, let me tell you that matrix multiplication A times B is only defined when the number of columns in A equals the number of rows in B. So you see, the sizes or the dimensions have to match up in this particular way. So they don't necessarily have to have exactly the same dimension. Like, it doesn't have to be that they're exactly the same size, but the number of columns in A has to equal the number of rows in B. Let's say if A is m by n and B is n by k. We're being pretty general here. We're just using letters for these. You can imagine that these are actual numbers. But notice here, I'm going to underline this a little bit. So notice that this is the number of columns in A, and this is the number of rows in B, and those are equal. I used the same letter for them, n. So the product, A times B, should exist. A times B is going to equal something. So what does it equal? Well, we're going to call it uppercase C, capital C, where C is also a matrix, but we have to say, well, what size is C going to be? Because A and B might have been different sizes, you know, like a rectangular matrix and a rectangular matrix, and then what size is C? It's actually going to be m by k, where the m came from the first matrix and the k came from the second matrix. So this is a discussion about how the sizes work, but what we really need to know is, how do we find the entries of C? If we say that A times B equals C, all right, well, that's fine, but how do you get the numbers that go into C? So entries of C are determined as follows. First, I'm going to try to summarize it in one or two sentences. and then I'm going to show you an example. The entry of C in row I, column J, is computed using the numbers in the ith row of A and the jth column of B. Makes sense that we would have to use both A and B in some manner. And we're going to say that we add the products of corresponding numbers. Now that sentence is really going to need an example. But this is a summary, but it really makes more sense once you see it. So let's go into an example with some specific numbers. All right, we'll move the page. So suppose I want to do, here, example. Suppose I want to multiply the matrix 1, 2, 3, 4 by the matrix 1, 3, 5, 4, 0, 1. And, you know, when you multiply two things, you can just put them side by side. You could put a little dot in the middle to say multiplication if you want, but it's optional. So, first of all, before we try to compute the product, let's just see if the dimensions match up. So the dimension of this first matrix is 2 by 2. It has 2 rows and 2 columns. And the dimension of the second matrix is 2 by 3. 2 rows, 3 columns. And is this product defined? Is this okay? Well, check this out. I'm going to underline this 2, and I'm going to underline this 2, just like I did earlier. These are the same number, and that means that this product is defined. You know, like when I said if A is n by n and B is n by k, and I underlined the n over here and the n over here. Yeah, they have to be the same number. So yes, this is defined. This does equal something. It equals a matrix, which we could think of as the matrix C. A times B equals C. And how big of a matrix are we going to get as the product? It's going to be 2 by 3, where I take this 2 that I did not underline and this 3 that I did not underline. So yeah, the product is going to be a 2 by 3 matrix. So we could kind of do something like this and leave ourselves some space to fill it in. It's going to be 2 by 3. So it has 6 entries, and we need to figure out what all 6 of those are. We have 6 entries, and I'll show you the particular method that we use. How about this? I'm going to kind of make 6 empty spots that we'll fill in. It's like 6 little problems. All right, normally we wouldn't draw like big bubbles there, but I'm just doing that because it's the first time we've done this. So we could look at each 6 of these. We could go from, left to right, top to bottom. So let's just start with the one in the upper left. This is the first row and the first column. I want to figure out what entry goes in the first row and first column. So first row, first column. The sentences that I wrote above, it said that we would look at the first row of A and the first column of B. Row 1 of A is this, and column 1 of B is this. right? It said it over here. It said, so the entry in row 1, column 1 is computed using the numbers in the first row of A and the first column of B. So I just wrote the first column of A and the first column of B. It says we add the products of corresponding numbers. So there's a 1, a 2, a 1, a 4. What do I mean by adding the product of corresponding numbers? Well, I'm going to say the first entry of this times the first entry of this, 1 times 1, plus the second entry of this times the second entry of this. That's what I meant by adding the products of corresponding numbers. First entry times first entry, second entry times second entry. This is 1 plus 8, so this is 9. And that 9 is the number that goes in this spot here. This is a 9. So we just figured out one of the entries in the product, and we need to do this for the other 5. So all we really had to do was, 1 times 1 plus 2 times 4. But the tricky part is recognizing that that's what we're supposed to do. It's this 1 times this 1 and this 2 times this 4 to get this 9. Let's move to the right one spot and figure out what goes in this spot here to the right of the 9. Well, in that case, we'd be looking at the first row and the second column of C, right? First row, second column is this spot. So what you do is you would look at or use the first row of A and the second column of B. And you do the same kind of thing. First entry times first entry, 1 times 3 plus 2 times 0. And you see what you get? It's a 3, and I'm going to put a 3 here. That's what we found. Let's move on to the next one. This is now, we're in the first row still. 9, 3 something is the first row. And we're in the third column. So first row, third column, and we're going to use the first row of A and the third column of B, which is 5, 1. And we're going to do 1 times 5 plus 2 times 1. And it's 5 plus 2 is 7, so I got a 7. I'll give you a chance to see that. Now, we figured out the half of it, right? We have the first row of the product, C. We need to figure out the second row. So now let's move on to the second row. We're going to do first column, right? So I'm focusing in on this one here. Second row, first column. So what we use is the second row of A, 3, 4, and the first column of B, which is 1, 4. So I'm going to do 3 times 1 plus 4 times 4. That's going to be 3 plus 16. I get 19. And I'm going to fill that in up here, 19. So hopefully by now you kind of see the overall pattern, like the strategy that we do. I'd like you to try to finish this. So maybe pause the video and see if you can finish the remaining 2 entries. Okay, so I just kind of left myself some space to do the work for each of these. As we get used to this, the more of these problems we do, the less we're going to need to write. I mean, we're kind of writing a big thing here, but we'll get used to it and it won't be so bad. All right, we're going to use this and this. So we get 3 times 3 plus 4 times 0 is 9. So let's put a 9 in that spot. And for the last one, you should have used the second row of A, which is 3, 4, and the third column of B, which is 5, 1. and you do 3 times 5 plus 4 times 1, and you get 19. So we put a 19 up here. And that's the product. We just did a matrix times a matrix, and we got the result is another matrix. This was all kind of the work that we were doing to get these numbers, these 6 numbers. And what I guess I'm suggesting is that in the future, I won't be writing this much, because I was trying to emphasize which row we needed to look at and which column we need to look at. In the future, we can just look at them. We don't have to write them each time. So we could have said, you know, okay, I'm going to focus in on this row and this column, or this row and this column, and just kind of match up the numbers we need to match up and just do that. So we'll do that in another problem. So before I show you another one, let me just say a quick note about the one that we just did. So note, we did this matrix times this matrix, and we got this matrix, 3, 7, 19, 9, 19. And I just want to emphasize the dimensions. So this was 2 by 2, this was 2 by 3, and this is 2 by 3. And in order to do this, these two numbers must be equal. If these two numbers were different, then you would just say undefined. The product does not exist. So, for example, if I were to try to do matrix multiplication of these two matrices, but in the opposite order, 1, 2, 3, 4. It's the same matrices, right? But this one is 2 by 3, and this one is 2 by 2. And if I take the number of, I guess this is the number of columns of the first matrix and the number of rows in the second one. Number of columns in the first matrix, number of columns in the second one, they're not equal, right? So because these are different, you just say it's undefined. All right, so now I'll show you another one. So I said that as we do more of these, we're going to write a little bit less. So that's why I want to do another one, just to show you how you could do this without writing so much. Let's compute A times B, where we are going to be given A equals 2, 3, 4, 5, and B equals, I'll do this one for us, and then pretty soon I'll have some examples for you to try. All right, there it is. Let's move this up to the top. I want to show you how I would typically do this without taking up half of a page. So I think what I'm going to do first is I like to take the two matrices that I'm multiplying and write them side by side. Helps me see how all the rows and columns are going to line up with each other. So I do that first. I do a quick mental check of the dimensions, and yeah, this is 2 by 2, this is 2 by 2, so I think that we're okay. And I think that the result that we get is going to be 2 by 2. Okay, so we can do this. The result here is a 2 by 2 matrix. Let's focus in the upper left entry. What do we need to do for the upper left entry? Well, it's going to be row 1, column 1. So we're supposed to use row 1 of A and column 1 of B. So I'm not going to write it all out. I'm just going to look at the 2, 3, and the 1, 0. 2, 3, and 1, 0. So it's going to be 2 times 1 plus 3 times 0. I'm just writing the work right here. That's my first entry. In the next step, I'm going to simplify it. It looks like that simplifies to 2, but I'm just going to simplify it in the next step. All right, what is the next entry over here? By the way, we can make this this bracket here. This matrix is a 2 by 2 matrix, but it looks like I'm making it look very wide. It's still just a 2 by 2 matrix. There's just going to be 4 entries in it. It's okay if it doesn't look like a square. All right, so in the upper right, I guess then we would be in row 1, column 2. So I need to look at row 1 of A, column 2 of B. So I'm looking at the 2, 3, and the 2, 1. 2, 3, and 2, 1. So 2 times 2 plus 3 times 1. Moving on to the lower left, I'm now in row 2. So I'm in row 2, column 1. So I need to look at row 2 of A, column 1 of B. So the 4, 5, and the 1, 0. 4 times 1 plus 5 times 0. 4 times 1 plus 5 times 0. See? And for the last one, we're going to look at, well, we're in row 2, column 2. So we're going to look at row 2 of A, column 2 of B. So 4, 5, and 2, 1. So it's going to be 4 times 2 plus 5 times 1. 4 times 2 plus 5 times 1. And now we can just fit this over here. Let's simplify all of those adding and multiplying. 2 times 1 plus 3 times 0 is 2. This is 4 plus 3 is 7. This looks like 4 plus 0 is 4. And this is 8 plus 5 is 13. So that's the answer. So you see, this is how much work I would typically show when I'm multiplying matrices. It's the same kind of work that we did before. Right? I mean, essentially, it's the same work. We just wrote a lot less. How about this? I'll give you some problems to try. Let's say that you are given A equals 1, 3, 0, 4, and B equals 2, 5, 4, 1. Don't multiply them yet, because I have multiple parts for this problem. Part A, I'm going to ask you to find AB. Part B, I'm going to ask you to find BA. And then part C, I'm going to ask you, does AB equal BA? So that's like a yes or a no question. Are they equal? So I'd like you to pause the video and give this a try. Okay, let's move this up. So, part A, let's put the matrices side by side. I think that helps us line everything up. Everything here is 2 by 2, so everything is defined. And a 2 by 2 matrix times a 2 by 2 matrix is going to give us a 2 by 2 matrix. So we can do this kind of like the previous problem. Let's see, row 1, column 1, I'm going to do 1 times 2 plus 3 times 4. Next entry is going to be 1 times 5 plus 3 times 1. Down here, 0 times 2 plus 4 times... 0 times 2 plus 4 times 4. And then lower right is 0 times 5 plus 4 times 1. And we'll simplify this. Should get 14, 8, 16, 4. That's the answer to part A. Part B, same matrices, but opposite order. We're going to see if that changes things. Okay, that's my setup. So let's just ignore what we did. Like, don't assume that the answer to part B is going to be the same as the answer to part A. Let's just forget about that for a second and just do the process. You know, we have the first matrix and the second matrix. We're going to use the rows from the first one and the columns from the second one. So 2 times 1 plus 5 times 0. I can already tell what the answer to part C is. Look at this. We already can tell that this entry is a 2. And this entry was a 14, so I can already tell that AB and BA are going to be different from each other. Over here, you should get 2 times 3 plus 5 times 4. Down here, you should get 4 times 1 plus 1 times 0. And over here is 4 times 3 plus 1 times 4. Altogether, this equals 2, 26, 4, 16. That's the answer to part B. So, part C, are they equal? No, not even close. They're not even close, right? No. They are not equal because 14, 8, 16, 4 is not equal to 2, 26, 4, 16. They would, in order to be equal, they would have to have the same entries in the same positions, and they don't have any of the same entries in the same positions. 14 is not equal to 2, 8 is not equal to 26, and so on. So what we've just learned is that the order matters. If you have two matrices and you're going to multiply them, A times B or B times A, you could get drastically different results. And that's interesting because usually in math, when we think about multiplying things, like if I were to multiply two numbers times each other, the order doesn't matter, right? If I do 7 times 5, I get the same thing as 5 times 7. And that's always true when you're multiplying real numbers. But when you're multiplying matrices, because of the particular way that we've defined matrix multiplication, AB is usually not going to be equal to BA. Usually. There are exceptions to that. There are some cases where they could be equal, but those are more of the exception to the rule. Overall, in general, I would expect them to usually not be equal. Let's see. I think we've got one more thing to discuss for this section. So far, we've learned how to add matrices, how to subtract matrices, what it means for them to be equal. And then we spent a while talking about how to multiply two matrices because that seems a little bit tougher. Not so bad, though. I want to talk about matrix multiplication and systems. Because remember, in the previous lessons, we were talking about solving systems of linear equations, and that seems to be the main topic overall for the past few lessons. It's only in this lesson where we started treating matrices just as these separate things, and we kind of forgot about linear systems for a while. So let me show you something here. Let's suppose A is this 3 by 3 matrix, 1, -1, 3, 1, 2, -2, 3, negative 1, 5. Let's suppose that the matrix B is this matrix 4, 10, 14. Look at this. This matrix only has one column. It might be the first time that we've seen a matrix that only has one column, but that's okay. It's still a matrix. And I'm going to have another one called capital X, and that is going to equal X, Y, Z. What I want to show you is that there's a connection between matrix multiplication and solving systems of equations. If we have these three matrices, then the matrix equation AX equals B is here's A, here's X. That's the order that I said to do them in. AX equals B. Okay, before we go any further, let's check to see, is this matrix multiplication defined? Like, is this okay? A times X. These look like they're very different sizes, different dimensions. Is it okay to do this? Well, this one is 3 by 3, and this one is 3 by 1. So yes, it is okay to do this because, look, this 3 is equal to this 3. Because they're the same, this product is defined, it does exist. And furthermore, I would expect that the result of multiplying them would now be 3 by 1. So this is a 3 by 1 matrix. So yeah, this is okay. All right, so all the sizes check out. If we perform the matrix multiplication, which I'm going to abbreviate, matrix multiplication, on the left-hand side of that equation, all right, what do we get? So I'm just focusing on the left-hand side right now. We're not going to use the right-hand side right now. Well, you know, how we've been doing this is you would take, to figure out the first entry, you would take the first row of this times the first column of this. Well, there's only one column of this anyway, so there's only one column that we could look at. But yeah, first row is 1, negative 1, 3, and then this is X, Y, Z. So I think I'm going to do 1 times X plus negative 1 times Y plus 3 times Z. That's going to look like X minus Y plus 3Z. That's my first entry. Now, I just want to point something out. This is one number. This is not like 3 different numbers. This is a 3 by 1 matrix, right? There's an entry up here, an entry here. Maybe I'll circle them. I'll do like a bubble around each one. The reason I'm trying to point this out is because what I drew here looks, it doesn't really look like as narrow as those other 3 by 1s. It's just because I needed room to write all those terms. All right, so you do that with these other ones. First row is done, so then you go to the second row, 1, 2, negative 2, multiply it by X, Y, and Z. You get X plus 2Y minus 2Z. And then for the third entry, we're looking at the 3, negative 1, 5, and you get 3X minus Y plus 5Z. Now, because this was an equation with a left-hand side and a right-hand side, now I am going to write it equals the right-hand side, 4, 10, 14. These are two matrices of the same size, so it is possible for them to be equal to each other. Remember, we said two matrices are equal if they have the same entries in the same positions. So the first entry of the thing on the left has to equal the first entry of the thing on the right. And the second entry has to equal the second entry, and the third entry has to equal the third entry. So I'm saying that x minus y plus 3z must equal 4. X plus 2y minus 2z must equal 10. And 3x minus y plus 5z must equal 14. All three of those things must be true. And what do we do when we have three equations that must all be true at the same time? We usually put a little squiggly bracket to the left of it, and we call it a system. All right, so this is a system of linear equations. In fact, I could be wrong. I'm not 100% sure, but I think this is a system of linear equations that we looked at in a previous lesson. I think if the 4, 10, 14 looks familiar to you, I think we might have solved this system in a previous video. So the point that I am making here is that ax equals b is another way to write this system. In fact, every linear system can be written as ax equals b for the appropriate matrices A, X, and B. So this is kind of a connection between matrix multiplication, which we just kind of did, and systems of linear equations. In fact, this is basically the reason why matrix multiplication is defined in the peculiar way that it is. This is why we multiply matrices in what might seem like an unusual way. It's so that we get this connection with solving systems of linear equations. But remember, if we wanted to solve a system of linear equations, we would still use the methods from the previous lessons. What I'm saying right here, it's not going to give us a new way to solve systems or anything like that. It's just kind of showing a connection between the previous lesson and this one. All right, so that was our lesson on the algebra of matrices. And so right now, you should be able to add matrices. If I ask you to add two matrices, subtract matrices, scalar multiplication, where you multiply by a real number, or maybe, some combination of those things. Like if I gave you a matrix A and I asked you, what is 5A? You should be able to find that. If I ask you, here are two matrices, multiply them together, you should be able to do that. Yeah, so these are the general size of problems that we would work with. It's usually, we saw some 2x2s and some 2x3s, 3x3, things like that. But the principles that we talked about actually apply to matrices of any size. One more thing I want to say before we wrap this up is that this lesson was called the algebra of matrices And we're going to continue to learn a little bit more about matrices in the next lesson also. But really, this is just an introduction. In this class, we're just doing an introduction to some of the things that you can do with matrices. There's actually a lot more that you can do with it. We have kind of an upper level math class that goes into more detail called linear algebra. This was called the algebra of matrices. And yeah, it's kind of the pre-calculus level of learning about matrices and linear systems. But I guess I'm just telling you that uh, there's a whole course devoted to it, so there's a lot that can go on with this. Anyway, you don't have to worry about that. So that's it for today, and take care. See you soon.